In today's lesson, we are going to look at time dilation derivation formula in the topic of special relativity. And we start with the thought experiment devised by Einstein, where he said, we imagine a source of light at the bottom being flashed to the top mirror. This is a mirror. And we imagine that it goes and comes back. And let's say this length is L. And so from our ordinary usual formula, we know that speed, that is the speed of light, is equal to displacement, which will be length L over the interval of time prime. We put prime because we want this to be the proper time. Proper time is that time which time interval which occurs when two events take place in the same spot, in the same space. The events in this case are the light signal leaving the bottom, going to the mirror and back. So going is one event and coming back is the other event, and if that happens in the same spot, we say that is the time interval taken, and as observed by a stationary observer here will be proper time. So this leads us to conclude that C times change in time prime is equal to L, and this would imply that if we square both sides, this would be the same as what we have there. Then now we imagine another same length of distance or displacement, but we imagine that the person at the spotlight which is being used is now moving to the right, and it is not stationary like it was here, but since it's going to move at uniform velocity, it is also still an inertial frame of reference. So we are dealing with inertial frames of reference, one which is either stationary or a moving one with uniform velocity. So in this case, a person who is outside this frame of reference, a moving frame of reference, will observe that the light does not just go to the top and back. He will notice that, or he or she will notice that when is here the light, when the spotlight is here, the light is actually here. But by the time the spotlight is here, the light may have moved a distance up. And by the time the light is, let me put it here, by the time the light is here, in this spot, the spotlight has reached that position. So instantaneously, we can see that the observation by this person outside in a stationary frame of reference who is observing this moving frame of reference will notice that the light takes this path to the top of the mirror and back through the other route. Of course, it comes back here. But to develop a formula relating what we have here with what we already found here, we can quickly see that we even don't need to work with that one first. We only need to say up to here. This person is moving with velocity v, and the time interval is this, it's not the same, but we don't know what that time interval is going to be, and we say we call that time interval change in t. So the displacement will be v times change in t. And we also know that from this spot, according to this observer, this displacement is going to be a displacement equivalent to c, the speed of light, times the change in t. So according to this of the observer, this is what he imagined, he or she imagines. So we can also work out using Pythagoras theorem that v change in t is, square plus L square should be equal to c change in t square. We know that L is the same, so we are going to say v square times change in t square plus L square is equal to c square plus change in t square. Since we know from this equation, let's call it equation 1, we know that this is equation 2. Since we know L is the same displacement, we can take the value equivalent to L squared here and put it here, and we find this will give us the formula v squared change in t squared plus L squared, which is now, it should be prime, sorry, I left out that, you can see it here. So that is c squared change in t prime square. We have just replaced L squared with this term, and this gives us c squared change in t squared, and so this gives us, we can collect the like terms, and we see that this term is change in t, this one is also change in t, so we could take this term that side and say c change, change in t, c squared change in t squared, subtract this term, which is v squared change in t squared, squared should be equal to what has remained here with it, which is c squared change in t prime squared. Looking at this, we can see that change in t is a common, so we can factorize that side and say change in t squared into v squared minus c squared is equal to c change in t prime squared. So from there we can now work out a formula. Quickly we can see that change in t squared is equal to, I'm just bringing what is there to this place, to this spot. What did I do here? It is c, sorry, that should be c squared, v squared, not the way it is now. Okay, this is c squared, v squared. Just made that error then. Now, so this is equal to that is equal to change in t squared is equal to c squared change in t prime squared over c squared v squared. And here we can see we could now say divide the fraction on the right by c squared both at the top and at the bottom, where we see this will be c squared change in t prime squared over c squared over c squared minus v squared over c squared c squared. In this case, you now have change in t squared, which is this one is going to give you change in t, because this will cancel out, and you have change in t prime squared over, or divide by. You can even do it this way, divide by. This becomes 1 c squared over c squared, and this is v squared over c squared. So now this is the equation you have, which is the same as change in t prime squared over 1 subtract v squared over c squared. And this is equal to what we have here. So you can now say change in t squared is equal to change in t prime squared, I'm just bringing it back here, over 1 subtract v squared over c squared, which we can now say take square root on both sides, and this becomes change in t is equal to change in t prime over the square root of 1 minus v squared over c squared. We have just taken square root on both sides. This leaves us with, this actually means this is change in t prime times 1 over the square root of 1 minus v squared over c squared. And this term, this part here is what we call, this one here, is what we call the Lorentz transform. And from here we can see that you are dividing the proper time by this fraction, and this fraction is smaller than 1. And a number that is the proper time divided by a number which is smaller than 1, the fraction which is smaller than 1, enlarges the right hand side, and therefore we say this is time dilation. In other words, that observer notices that it doesn't take the same amount of time as a stationary observer.